And I'm taking a look at problem number 3. Okay, I'm going to read this. In a recent survey of 9 randomly selected subjects who identified themselves as Buddhists, the following responses were collected for the number of hours daily spent watching TV: 0, 5, 0, 1, 2, 1, 3, 2, 0. Using Excel, calculate the mean, standard deviation, and standard error for this sample. Okay, use this information to calculate the 95% confidence interval for the mean number of hours watched of TV watched by all U.S. Buddhists. Repeat the calculation using SPSS. So we're going to get a look at a couple of these things. And SPSS is also going to give us some more insight into this as well. What assumptions did you make for this analysis to be valid? Well, we're about to take a look at this. Okay, so now, first of all, let's start off with that. What assumptions are we going to be making about this distribution if we're going to attempt to calculate a margin of error and a confidence interval for this mean? Okay, where in other words, we're going to be working with sample distribution for samples of size 9 for this particular calculation. And in fact, there are nine values there, right? Okay, good. I think that came up on one other problem. Okay. What do you think our assumptions are? What's our first assumption? Okay, how were these Buddhist samples? Did we sample only Buddhists that had flat screen TVs and ignore all the other Buddhists that might have the old style cathode ray TVs, or do we survey only ones that lived in New York and so on and so forth? Well, what we attempted to do is to get a random sample of all Buddhists, right? So that's number one assumption, is that we have random sample. The other assumption that we make is that the distribution of the number of hours that Buddhists watch TV in the United States is normally distributed. In other words, it's not like 90% of all Buddhists are watching it for 2 hours, and 10% are watching it for 3 hours, and 5% for 4 hours, and so on and so forth, and none are not watching it at all. It isn't a terribly skewed distribution. Now, the central limit theorem tells us that even if this distribution were not absolutely perfectly normally distributed, we can still assume that repeated samples, the mean of repeated randomly selected samples of people from this population, the means of the sample results of those means, the distribution of the sample results of those means, even though the original distribution is not perfectly normally distributed, then we can assume that that we do have a normal distribution for the sample means. Okay, that's that. What we're saying there is that this methodology based on the central limit theorem is robust. That we can use it in a lot of situations where we might be concerned if we didn't have a perfectly normal distribution of values within the population. Okay, so that's basically our main assumptions: random sample, and that the original population is roughly normally distributed. Okay, so let's take a look at this. Let's take these values and put them into Excel. Okay, and I'm just going to take it, and I'm literally going to type them in here. Okay, and you guys, if you have, you can probably, you're watching this in a window at home, so you can, just as I am, you can pull up an Excel spreadsheet or something like that and actually type these values in as well. Or you can sit back and have an espresso and watch me do it. Let's see, excuse me, 1, 2, 1, 1, 3, 2, 0. I'm balancing a few things here, like my graphics tablet and so on and so forth. So it's kind of hard for me to type 050121320. That looks about right. Okay, so next thing I'm going to do is I'm going to calculate the values that it asked me to. I'm going to calculate the mean first. Okay, and the mean is 1.55. I'm going to calculate the standard deviation for my sample, which is 1.67. And then I'm going to calculate a standard error. I'm going to type that out so that we can distinguish that from the standard deviation. The standard error is the standard deviation of the sample results of size 9. It's dependent, in this case, standard error for a sample size 9, right? It's not a standard error for any other distribution of means. It's standard error for if you repeatedly took samples of size 9 from this population. What's that going to be equal to? It's going to be equal to the standard deviation of the population, which we really don't know. So we're going to use the standard deviation of the sample to estimate the standard deviation of the population, divided by the square root of the sample size, n. Okay, so now I'm just instead of, I'm just doing that to illustrate what it's going to look like. But if I'm actually going to put it in here, I'm going to substitute for this. I'm going to actually put in the value 1.67, and I'm going to put in the value of the square root, which is that we're looking for, of 1.666, and so on. Okay, and I think I'm okay there. Let me give it a try. And okay, square root of did I put in? Excuse me. I don't know if I put in 9 there. I put in a 12 again. I wanted to put in the number 9. Let me do that again. Equals 1 point. Whoops. Again, I'm trying. Let me put this thing down here so I can actually type. Equals standard deviation divided by the square root of the sample size, which is 9. Okay, good. Did anybody catch that? I see now you guys are sleeping there because you're not helping me out by like catching me right away when I do this stuff. Okay, so that's our standard error. Okay, so our sample means are distributed with this standard deviation, which we call the standard error. So now I'm going to go back here and I'm going to say, well, what's it asking us to do? It's asking us to calculate those values, right? This is what we've just done so far. Okay, then it's asking us to use this information to calculate the 95% confidence interval for the mean hours of TV watched by all Buddhists. Okay, so I'm going to go back here. Okay, so now I'm going to calculate our 95% confidence interval. Okay, well, a 95% confidence interval is going to be equal to the mean plus or minus the ZT score. In this case, it's going to be T-score for a probability of 0.05 because we're looking for alpha. Oops. Equals 0.05. We're looking for a 95% confidence interval, so we're willing to accept a 5% chance of error, an alpha error of 5%, times our standard error. Okay, so this part of this equation, the t-score, right, for alpha equals 0.05 times the standard error, that's our margin of error. We're going to subtract and add that to the mean to get our 95% confidence interval. Point estimate is the value that you're predicting the mean to be. Okay, in other words, based on this sample, right? Based on this sample, we estimate that the mean of the population. Remember, the reason why we're sampling is we're trying to predict the mean of the population, not because we really want to know the mean of those particular 9 people. So our estimate of the mean of the entire population is 1.55. That's our point estimate. If I were to tell you that we sampled 10 people in a population and 3 of them were diabetic, our point estimate, the prevalence or the percentage or proportion of people that had diabetes in that case would be 0.3. That would be a point estimate too. It's an estimate of what the entire population represents, but as a single point. Now that doesn't have too much meaning because when I tell you that the mean is that our estimate of the mean is 1.55, you don't know how accurate that is. In other words, if I didn't give you information about how variable the values were, the mean may be 1.55, but I'm not telling you if some values were 0 and some values were 20 and some values were 30 and so on and so forth. there may be other, since you don't know those variables, or you may not know those variables, just got a warning that like I might have a little problem with audio and stuff like that. Hopefully you're hearing me okay. Um, so we need a way to describe how accurate that reading is, not just what that point estimate is. That's where the confidence interval comes in. The confidence interval gives us a range that we know that we're 95% certain that the real mean is between these two numbers, which in a lot of ways is a lot more powerful than guessing that the mean is exactly this number, right? It's a lot more useful to us. If not, then maybe not more powerful, but more useful to us. Okay, so let's calculate this. So it's going to be the mean is going to be equal to 1.5. So the mean is going to be equal. I'm going to calculate the margin of error first. Okay, what's our t-score that we're going to have to use for this sample size 9? Well, I'm going to go back here. Let me see if I can't get to this. Let's see. Okay, let's see. I think I have a t-table here somewhere. And I think this is my t-table. Here's our t-table. Okay, I could get it from Excel also, but I want to use this table. Okay, our sample size is 9. If our sample size is 9, our degrees of freedom is 8. Okay, so I'm going to look for my t-score on this t-distribution table. I'm going to look for my t-score in the line that represents a sample size of 9 or degrees of freedom of 8. So I'm going to go across from here. And I'm going to go down here for the column that represents a 95% confidence interval. In other words, 5% chance of being wrong, and it won't be in that interval, the real mean. However, if you describe it as the probability in the tail, right, it's 5%, 2.5% in the left tail, and 2.5% in the right tail of the distribution. So it's a t-score for alpha equals 0.025 in the right tail. Okay, we know that since we almost always do two-tail tests, that a t-score for 0.025 in the right tail is the same thing as a two-sided t-tail of 0.025, also 0.025 in each test, or 0.05 overall. Okay, but in any case, they make it simple for you by just telling you the confidence interval up here. If the table only showed these numbers down here, you'd have to remember that if they're only talking about one tail, then you have to look for the one that says 0.025, because then you're accounting for the other tail as well in your 5% error, possible error. Okay, so let's go across to here, and the t-score we need to use is 2.306. Everybody comfortable with getting that t-score? Margin of error equals 2.306. Everybody comfortable with that? Can you guys still hear me there? Just someone just type in again to make sure that you can hear me. Okay, good. You got me worried there for a second. All right. I did get a warning before that the audio might be degrading because there's a little bit of lag on the internet right now. Okay, so 2.306 times the standard error, and we just calculated the standard error to be 0.555. So our margin of error is equal to 1.28. So let's take a look at what we have now. Our mean, if I want to calculate our 95% confidence, that's going to be equal to our mean, which was 1.55, plus our margin of error, in other words, t times our standard error, is 2.83, or it's equal to our mean minus our margin of error. So our 95% confidence interval for the true population mean is going to be 0.27 to 2.84. Okay, that's our 95% confidence interval. And 95% sure that the real mean, real average number of hours of TV watched by this population is between these two numbers. Okay, our point estimate was 1.55, but our confidence interval was between these two numbers. Okay,